Welcome to day 2 of MIPI DevCon 2020. We're glad to have you back. Feel free to interact with the presenters and attendees by using the engagement tools at the footer of your screen. Use Q&A to engage with the presenters and group chat to communicate with attendees. You can minimize and maximize each icon by simply clicking on each icon. To view the agenda and see the sessions and demos for today, click on the call to action icon. Enjoy the conference.
Hello everyone, my name is Licenia Souza. I'm a product marketing manager at Synopsys for MIPI IP. And in the next 25 minutes or so, I'll be talking about why an integrated MIPI C-PHY D-PHY IP solution is essential. So here's the agenda. I will start by giving you my perspective about the most relevant MIPI camera and display market trends. Then we will move the discussion to the specs, how these are evolving to address the growing imaging needs. And then finally, I'm going to share a few use cases that we have been exposed to, some of our customers that are already using a C-PHY, D-PHY in their designs. So starting with the camera continues to innovate to address the growing vision processing needs. Well, if the focus in the past was around the human vision, today that's still the case, but it also continues to evolve to address the requirements for machine vision applications. So in terms of the most relevant trends, starting with the fact that we already have these impressive image sensors supporting more than 100 megapixels. The idea here, according to some vendors, the goal is to continue evolving here up to 600 megapixels, which is quite impressive. The AI-enabled image sensors, so these image sensors with built-in AI capabilities, these are already available. And well, mobile continues to require more pixels, more image sensors, and bigger image sensors. So the requirements continue to evolve here. In automotive, well, vision systems are at the heart of automotive, ADAS and IVI. There are a number of applications in automotive inside a vehicle that require different image sensors with different attributes, whether it's dynamic range, signal to noise ratio, resolution, size, power, and some of these peripherals image sensors are that need to be automotive grade. In fact, there are already a few vendors that already have automotive grade image sensors. So a lot of image sensors are combined with other sensing technologies. There is an example, I think it's public from Waymo, where they combine up to 30 image sensors with LiDAR and radar. Besides automotive, there's everything else. IoT, call it Internet of Things, or intelligence of things, edge applications, MCUs with vision capabilities, machine vision capabilities. Here's an example from NXP, an MCU with face recognition that is being marketed for home applications, home appliances. Now, moving to the display innovations are being driven by typically by mobile and automotive applications. Things like dual display, foldable displays, high refresh rates, high resolutions. Those are things that we see being deployed in mobile, in AR, VR, and also in automotive. And in the case of automotive, there are indeed a number of applications where MIPI displays are a good fit. Typically, these small form factor displays for in-mirror or rear view, or even other displays in the clustered small form factor displays. These are definitely a good fit for MIPI DSI displays. Then there's everything else, consumer, industrial applications that can still leverage the fact that MIPI displays are widely available and enable a low-cost implementation. Moving to the spec, how are the camera and display specs evolving to address the imaging needs? So obviously we all know that MIPI CSI is for camera interface, and it uses both D-PHY and C-PHY for the physical layer as options, or both. And the same happens with MIPI DSI-2, which is for display interface and uses also D-PHY and C-PHY as a physical layer. Starting with the physical layer, here on the left side, MIPI D-PHY, very well known, widely adopted. Majority of the applications today still use a D-PHY for the physical layer. It's a relatively simple implementation, source synchronous architecture where you have the clock lanes and the data lanes. Sorry, we have the clock lane and the data lanes. The high speed, and it has high speed and low power modes for efficiency. High speed for the actual data that you want to transmit, and low power modes for control and handshake. Again, it's proven, mature, and widely adopted. Here's an evolution. Today, it started way back, 1.5 gigabits per second per lane. And today we are at version 2.5, supporting up to 4.5 gigabits per second per lane. The next version is in the works and expected to come later this year, and it will target the 9 gig. On the right side, MIPI C-PHY, the cousin, it was developed to achieve higher bandwidth transmission on restricted channels. Things like chip on glass, chip on film, or chip on plastic. The key concepts are trios and the three-phasing encoding, and all the rules on top of that in terms of encoding and mapping. With that, the bit rate is approximately 2.28x the signaling rate. So you're effectively sending more bits per transition, more information per transition. If you look at the diagram, you'll see that the transmitter is looks like a single-ended driver, single-ended transmitter, and the receivers are differential, which is unique, but everything works fine because of the rules in terms of encoding and mapping that make sure that everything works in concert. These three wires work in concert. There is no contention. There's always 100% transition density that is guaranteed, which kind of helps with the receiver implementation. In terms of the timeline, 2.5 gig version 1.x, and today version 2.0 already supporting 6 gig symbols per trio, which is quite impressive. Now, what is the recommended approach? Well, the recommended approach is to combine the best of both worlds, and that is possible with an integrated MIPI C-PHY D-PHY solution, a combo solution. And why is that possible? This is perfectly possible because both have the electrical specs are quite similar. The low power modes are identical. Most of the circuits can be reused, and you can actually share, they can coexist in the same pin. So 10 pins, for example, with 10 pins, you can have 4 lanes and or 3 trios. So that's perfectly possible. If you look on the right side, what I show you here is a simple implementation, a simple example where you have the protocol stack here, whether it's CSI-2 or DSI for display, and this box here shows you the combo solution, MIPI C-PHY, D-PHY. In this case, you have a D-PHY mode with 4 lanes, and the clock lane connected with the image sensor. In this case, would be in D-PHY mode. But with the same design, with the same implementation, with the same hard macro, you can actually configure it and operate this in C-PHY mode up to 3 trios and leveraging the same pins. So in this case, you would be connected to an image sensor that supports C-PHY, or an image sensor that supports both D-PHY and C-PHY. That's also possible. This approach will effectively satisfy most of the important KPIs in terms of maturity. It comes from D-PHY, the fact that it's widely available and proven, the backwards compatibility, the fact that this approach allows you to support both C-PHY and D-PHY, the flexibility, again, to supporting both protocols. Also on the flexibility point aspect, the fact that C-PHY with the fact that it has an embedded clock, enables some flexibility in terms of how you connect the devices, right? So you can actually connect one device to one trio, or one device to multiple trios. So those arrangements are possible, and that's quite interesting for some of the implementations. It enables performance, right? So D-PHY has a very good bandwidth, supports good bandwidth. C-PHY improves that a little bit, so that boost of performance comes with the C-PHY D-PHY implementation. Power efficiency in C-PHY, as I mentioned, you're effectively sending more information per transition. So if you look at the energy per bit, you will see some efficiencies as you operate in C-PHY. The reduction of emissions. With C-PHY, there is no dedicated clock lane, and it's embedded clock, so that will contribute to a significant reduction of the emissions. Now, looking at the protocol above, starting with the camera CSI-2, which continues to evolve from a mobile-centric to effectively a vision platform servicing a variety of use cases. So if you look at the beginning, the focus was more in enabling the high resolution, frames per second and bits per pixel. This all translates into bandwidth. Then it evolved to add additional capabilities to address different use cases. We're looking at virtual channels, the ability to tag different payloads coming from different sources. So this is interesting for aggregation when you want to aggregate multiple sensors into one stream. The power spectrum density reduction. So there are capabilities to reduce the emissions and to allow these image sensors to be placed closer to sensitive circuits. LRTE, this is an improvement, latency reduction and transport efficiency. And so basically this allows you to aggregate more information in a more efficient way. And DPCM, this is a sophisticated compression algorithm that will obviously translate into bandwidth savings, but keeping these important attributes of the image that are required to be consumed by these machine vision algorithms. RAW 16 and 20, these are additional advanced data types to enable high dynamic range. The version C 3.x continued to evolve and added additional capabilities, USL, the ability to basically bring the sideband interface into the same link, dropping that, so saving those pins. It builds on top of LRTE, so it also enables longer channels beyond the traditional 30 centimeters. And the smart region of interest, this is quite interesting. This allows you to send a portion of the image, what is relevant. This is particularly relevant for machine vision applications, for factory automation kind of applications where the scene is constant and you're just looking at some of the transitions. So you can actually only transmit the portion of the scene that is changing, and that obviously translates into significant savings in terms of bandwidth and power. And then RAW 24, basically evolving from 1620 to RAW 24, important for these applications that require high dynamic range. In terms of the next version, the focus will be automotive, bringing in some native functional safety features, the support, the interaction with the PHY, the new spec that was recently announced. There's this interesting use case, always-on sentinel control, the interest of having this, for some applications, for some use cases that require some always-on capabilities, using a low bandwidth, low power link that is always active, and if the application sees something that it's relevant, it can switch to a C-PHY, D-PHY link. So this is also an interesting capability that is coming soon. And then obviously for me, there's additional capabilities being added for content protection and security. On the DSI side, the de facto interface for embedded displays. The pace of innovation, I'm trying to summarize it here. The first version, again, also focused on mobile, but evolving to address more applications that require embedded displays. And so we're looking at the beginning, the focus on enabling high resolution frames per second and bits per pixel, and combining compression to overcome any limitations to effectively reduce the bandwidth that it's needed and the power consumption associated with that, and be able to transmit high resolution content. So VESA DSC 1.1 was introduced here, and this enables a compression factor of 3 to 1 with 8 bits per pixel. The current version 1.1, has capabilities again for power spectrum density reduction, again to place these devices closer to sensitive circuits, and it adds support for VESA VDCM which enables compression up to 5 to 1 with 6 bits per pixel. If we look at MIPI DSI-2, the next version, in terms of what is in development, the next version of the spec the focus will be around content protection, automotive capabilities, bring in native functional safety capabilities into the protocol, the interface with MIPI C-PHY, and other features that are also being worked on. For example, one which is very interesting, associated with adjustable frame rate, which will enable significant savings in terms of power. Switching to some of the use cases that we have been working on with our customers. So here's an example in mobile. Two solutions, one for camera and one for display. So the first one is a image signal processing between the camera and the application processor with the MIPI interfaces on the input and output using C-PHY D-PHY combo. This chip here, it brings AI capabilities into this chip. So effectively, some of these applications, they, from an application point of view, it requires some AI capabilities, and this chip basically brings them into hardware. So these capabilities are accelerated in hardware. Then this example for the display, it's basically a video image processing for the display, also with the C-D-PHY on the receiving end between the application processor and the display. So there's a receiver and a transmitter, and then obviously the logic from our customer to enhance the display quality. So things like improving the refresh rate or increasing significantly the refresh rate. Another interesting use case, this is a drone from DJI using Synopsys DesignWare C-PHY, D-PHY IP. Obviously, drones are a very interesting application. They use a variety of MIPI sensors combined with other sensing technologies for navigation, but they also need a really high-resolution image sensor to capture the scene, right? And so, in this case, what we helped DJI with our IP to connect with one of the most sophisticated image sensors that is available today, operating an image sensor with supporting 64 megapixels. And we're able to interoperate with that image sensor up to 3.5 gigasymbols per second. So here's an image of our labs. This is our setup, our test chip in 12 nanometer connected with that state-of-the-art image sensor, and then looking at the C-PHY traffic here on the scope. Moving to automotive, where this diagram, the idea is to show you where MIPI IP is being used, MIPI CSI-2 for sensors, and also DSI for display interface. So starting with the display, there's a number of these display applications, in-mirror, rear view, or even some of these cluster displays that connect with the SoC typically with a long channel, long reach technology. The same happens on the CSI side. So for example, an ADAS application where image sensors are combined with other sensing technologies like radar or LiDAR, and they are aggregated, and then they are connected to the application processor, again with a long reach solution. And then the parking assistance with where multiple image sensors are aggregated, and then that information is fed to the application processor. When you talk about automotive grade IP, it's different from commercial grade IP, and effectively there are three fundamental pillars that need to be addressed. The functional safety, so basically we need to develop the IP to make sure that we can help our customers achieve their target ASIL levels. What that means is that the IP itself also needs to target those ASIL levels. And again, what that means is that we need to do the necessary changes and updates to the IP, add additional capabilities, functional safety capabilities to make sure that the IP is able to target to achieve those ASIL targets. From a reliability point of view, the PHYs, they need to be designed with the automotive tech files from the foundry, and then the silicon also needs to be qualified, make sure that it passes all the ACQ 100 qualification so that our customers can actually do the same. All this needs to be done with a rigorous quality control system process where traceability is of paramount importance. Here in automotive, we also have an interesting use case. This is one of our customers, Valence, which is using DesignWare C-PHY, D-PHY solution for their next generation long-reach CSI-2 connectivity, right? So Valence, their technology, Valence Automotive Technology, enables in-vehicle high-speed links for cameras and sensors with long-reach CSI-2. So we have the image, the sensors, whether it's an image sensor or other sensing technologies that can still leverage CSI-2 as a transport. Then this chip, the Valence chip, the technology will basically convert that into an A-PHY interface, and then there's another chip on the other side that will translate things from A-PHY to CSI-2, which then connects to the SoC. In summary, What we talked today, we talked about the most relevant market trends, my perspective about the most relevant market trends for camera and display. We talked about the importance of an integrated C-PHY, D-PHY solution. And then we talked about some of the use cases that we have been exposed based on what our customers are doing with our IP. So at Synopsys, we have a comprehensive solution for both camera and display, a complete solution with controllers and PHYs, whether it's D-PHY-based solution or C-PHY, D-PHY-based solution, the combo controllers. This is a solution that is available from 40 nanometer down to 5 nanometer. It supports up to 4.5 gigabits per second for D-PHY, 3.5 gigasymbols for C-PHY. It's available as a commercial solution for commercial applications and also for automotive applications. We have Automotive Grade IP, ASIL-B ready, and a Grade 2. It's a solution that is adopted by multiple customers across the board in different applications, and whether it's mobile, drone, DSC, and surveillance IoT. So if obviously if you need more information, please don't hesitate in reaching out to Synopsys, and we'll be more than happy to continue the discussion. With that, thank you very much for your time. I really hope that you're staying safe and healthy in these challenging times, and I hope you continue to enjoy this year's MIPI DevCon. Thank you.
Thanks, Lucinio. I encourage questions to come into the Q&A pane, and see that we have a few already, so we'll get straight to it. How is the adoption of 2.G versus 3.5/4.5?
Very good. That's a good question. Hopefully you can hear me. I would say that the majority is still at 2.5 gigasymbols, gigabits, mainly D-PHY. C-PHY adoption is definitely increasing. On the display side, typically around 2.5 gig. Camera is the use case that requires higher bandwidth. Applications such as mobile, drone, and automotive are looking at data rates beyond the 2.5 gig. So 3.5 gig, 4.5 gig are becoming a good fit for these applications.
Thanks. What are the relevant CSI-2 features for automotive applications?
Absolutely. That's also interesting. We covered that a little bit in this presentation. I kind of went through that very quickly. But definitely on the physical layer, both D-PHY and C-PHY for automotive makes total sense. The data rates at 2.5 gig, but also some, actually we have some customers that are already using at the 3.5, 4.5 gig. So definitely both D-PHY and C-PHY in terms of physical layer. In terms of protocol, well, CSI-2 spec includes a number of capabilities that are targeted for automotive applications, not just automotive applications, but if we look, for example, the raw data types to enable the high dynamic range use cases, very important for automotive beyond 120 dB. The virtual channel, so it's been around for quite some time, but this is an important capability that enables aggregation of multiple sensing technologies, or even for one particular sensor to be able to handle multiple exposures, tagging that in the same link and distinguish those exposures. And then LRTE, it's again latency reduction and transfer efficiency. We're talking about aggregation, so it's how much data we can pack in the same link. And so these protocol improvements, they definitely help with aggregation, which is relevant for automotive applications.
Thanks, Lucinio. Next question is, what are the relevant CSI-2 features for, I'm sorry, I apologize, I just read that question. Is 3.5/4.5 really needed for display?
Well, that's an interesting one for sure. Well, the demand for bandwidth is definitely there, right? But indeed, there are challenges related to the channel, chip on glass, chip on film, chip on flex. to achieve those data rates. There are, as far as I know, there are indeed developments to remove those channel restrictions to increase the data rate. In the meantime, C-PHY is the path to increase the bit rate because for a given signal rate, we can actually achieve a 2.28x in terms of bit rate. And then adding on top of that, the compression, right, the VESA DSC with the visually lossless compression, it's also another option to reduce the bandwidth requirements when targeting high resolutions effectively.
Okay, thanks very much, Lucinio. Unfortunately, we are out of time, but thanks again to you and for the attendee questions that came in. I encourage you to go to the Engagement Hub to see the upcoming sessions, and thanks again.
All right, have a good one, everyone. Enjoy the MIPI DevCon this year. Thank you.